evolution. Applications inevitably change over time. Features are added or modified as new products are launched, user requirements become better understood, or business circumstances change. In Chapter 1, we introduce the idea of evolvability. We should aim to build systems that make it easy to adapt to change. In most cases, a change to the application's features also require a change to data that it stores. Perhaps a new field or record type needs to be captured, or perhaps existing data needs to be presented in a new way. So basically, when the data change, the application also needs to adapt to it. And another thing is that based on all of our previous conversation, to connect this to OS, TCP/IP, data structures, and algorithm, if you will notice, there's one theme that keeps reoccurring, which is the abstraction and the anti-fragility or the evolvability of systems. Because if you think about it, in order for a system to become big, there's need to be some manageable layer, or each layer should be manageable, because if not, you will not be in control of the system, and it's gonna hard to have a mental model, or to keep in touch or to make sense. I don't know. I think there's some word to it. I guess it's like the understanding of the system. Those understanding makes us sane, or at least not make us crazy. So those are actually the recurring theme. So this we will discuss the encoding and the evolution. How do we decide a data format that will allow us to transfer data in different layers? So that's what we're going to discuss here. The data models we discussed in Chapter 2 have different ways of coping with such change. Relational databases generally assume that all data in database conforms to one schema, although that schema can be changed through schema migrations, i.e. alter statements. There's exactly one schema in force at any one point in time. So a schema is basically how the tables on your database connect. So remember, tables is just a row. We just put a column to it in order for us to distinguish each row and for us to make sense of it. Now, let's see here. Let me just read what the actual schema means when it comes to database. So think of it like a folder inside a database. Simple definition: a schema is a named collection of database objects such as tables, views, indexes, functions, and procedures. It helps you organize, secure, and reference objects cleanly. Analogy easy to remember: database is equals to house, schema equals to room, table is equals to furniture, or table is equal to document. Or for programmers, schema.table is like package.class. Example: so suppose you have database called company underscore db. Inside it, you might have a schema like public, sales, HR analytics, and tables like sales.orders, sales.customers, HR.employees, analytics.daily underscore metrics. Each schema can have tables with the same name without conflict: sales.users, HR.users. Why schemas are useful? First, organization. Keep things tidy. Auth that users, app that post, logs that events. Instead of hundreds of tables dumped together, you kind of organize those tables on how they are related in a global state and also in a local state. Just like with PostgreSQL related to Redux, security and access control. You can grant permission per schema, grant select on schema analytics to analyst underscore role, so users only see what they're allowed to. So it's you can also think of it like the dimension table and column storage. So you can provide an access to those dimension only to your users. Name spacing, third, avoid collisions. Two teams can both have users table. Auth that users, billing that users, no conflict. Fourth, cleaner migrations and maintenance. Drop or migrate a whole module easily. Backup parts of the database logically. Is schema the same as database? No. Term database meaning top level container. Term schema meaning namespace inside database. Term table, data structure inside schema. So table is just a data structure in the end. It could be B trees or it could be what do you call that? It could be B tree or it could be LSM tree. Right, so common database says in schemas database PostgreSQL, default schema public database SQL Server, default schema DBO, database Oracle, default schema user equals schema, database MySQL, default schema equal database, terminology overlap. Real world example, PostgreSQL slash Supabase, create schema block semicolon, next line create table block dot post, open parenthesis, next line ID UID primary key comma, next line title text capital X comma, next line content capital text, next line close parenthesis semicolon, reference and select asterisk from block dot post semicolon. When you should care about schemas, since you've been working with SQL scripts, Supabase or PostgreSQL backends, you'll use schemas to separate auth versus app data, control access, avoid naming conflicts, structure large projects cleanly. One sentence takeaway: a schema is a namespace inside a database that organizes and controls database objects. So that's the schema. So when a data format or a schema changes, a corresponding change to application code often needs to happen. The data models we discussed in chapter 2 have different ways of coding such change. Relational database generally assume that all data in database conforms to one schema. So as we discussed in the previous chapter, different interfaces or different language are used to interact with this database structure or those different schema. Relational databases generally assume that all data in database conforms to one schema, although that schema can be changed through schema migrations like other statements. There is exactly one schema in force at any one time. So though you can change schema, I mean it's not that easy, especially in a relational database, because those schema is what makes those intact, like that makes it organized and easy to retrieve, because the purpose of database is for us to be able to query it and return as the result. When a data format or schema changes, a corresponding change to application code often needs to happen. For example, you add a new field to a record and the application code starts reading and writing that field. Like with my Redux, to like if you change some format on your data, you need to be able to update your interface, your TypeScript interface, as well as slice.ts for Redux, because those are the application code that are adding a new field or reading and writing that. However, in a large application, code changes often cannot happen instantaneously. With server-side applications, you may want to perform a rolling upgrade, also known as stage rollout, deploying the new version to a few nodes at a time, checking whether the new version is running smoothly, and gradually working your way through all the nodes. This allows new version to be deployed without downtime, and thus encourage more frequent releases and better evolvability. So these are always recommended for large application. You change one small step at a time, and then you iterate. So remember, we're changing the database here, not the application code. You can think of the database as kind of the data that we fetch to the code stream and execute on the CPU execution. So those are one of the metaphors that will allow you to understand that. So the data is separated to the code, right? But changing that ultimately needs to be synchronized with your code because the codes are executing the data. With client-side applications, you're at the mercy of the user who may not install the update for some time. This means that old and new versions of the code and old and new data formats may potentially all coexist in the system at the same time. In order for the system to continue running smoothly, we need to maintain compatibility in both directions. So these are the where we will introduce the backward and forward compatibility concepts. For backward, newer code can read data that was written by older code. For forward, older code can read data that was written by newer code. Backward compatibility is normally not hard to achieve. As author of the newer code, you know the format of data written by older code, and so you can explicitly handle it if necessary by simply keeping the old code to read the old data. So backward compatibility is easier. Forward compatibility can be trickier because it requires older code to ignore additions made by a newer version of the code. In this chapter, we will look at several formats for encoding data, including JSON, XML, protocol buffers, TRIF, and Avro. In particular, we will look at how they handle schema changes and how they support systems where old and new data code need to coexist. So, think about this as before we discuss how the storage engine decides based on how how the principles of the storage engine of different database actually works under hood. And now we're talking about kind of like the application layer interface on how we will create those database, the schema, or the table, or the document. Now, in particular, we will look at how they handle schema changes. So remember, this data is what we ultimately put as a row or document in the database. So this data or this data format, the data format that actually we will use will dictate the schema or the organization of our data. In our case of our Supabase and Redux, we actually use JSON because Redux, it's more easy because Redux are already JavaScript and JSON is also a JavaScript. We will then discuss how those formats are used for data storage and for communication. In web services, representational state transfer and remote procedural calls, as well as message passing systems such as actors and message queues. So we will discuss how this format are being converted uh, throughout web services, because remember we have UI, the front end, and then the back end actually accept that request, and then the back end then contact the database. So how do you connect to that? So of course, you're gonna use protocol, and that's what the REST is for. So how do those data format use this protocol, or communicate using this protocol, such as REST, and remote procedural protocols such as RPC, as well as message passing systems such as actors and message queues. So how does it execute in message queues, etc. So this is also how you would understand how those, like, transferring of data, such as earlier I'm having a problem of projecting the monitor of my phone, Huawei phone, to my PC, because I actually was I can easily project my Oppo phone because it's using Android, but for Huawei it's a little bit trickier. So that's where an understanding of like remote protocol really helps, or this protocol like to transfer data and project to screen really help to troubleshoot the issue. Now, formats for encoding data. Programs usually work with data in at least two different representations. First, in memory, data is kept in objects, structs, lists, arrays, hash tables, trees, and so on. So this is what the programmers see. This is how what you would construct in memory, or what you would define using your code in your memory. Uh, these data structure are optimized for efficient access and manipulation by the CPU, typically using pointers. So that's where the OLAP, or transaction database, are. So it used pointers for efficient later optimized access for when we transfer now into database. Second, when you want to write data to a file or send it over the network, you have to encode it as some kind of self-contained sequence of bytes. For example, a JSON document. So a JSON document to Firestore, for example, to database, since a pointer wouldn't make sense to any other processes, the sequence of bytes representation looks quite different from the data structures that are normally used in memory. Thus, we need some kind of translation between the two representations. The translation from in-memory representation to the byte sequence is called encoding, also known as serialization or marshalling, and the reverse is called decoding, parsing, deserialization, and marshalling. As this is such a common problem, there are myriad different libraries and encoding formats to choose from. Technology clash. Serialization is unfortunately also used in the context of transactions, see chapter 7, with a completely different meaning. To avoid overloading the word, we'll stick with encoding in this book, even though serialization is perhaps a more common term.